All right, I think we've probably gotten to a reasonable number. We're at 71 people on the call. So
Okay.
I will start us off. All right. So welcome everyone, and thank you for joining CARB's meeting for the Soil Nitrogenous Emissions Subject Matter Expert Review Panel Final Report. My name is Kevin Esslinger, and I am the staff person in CARB's Air Quality Planning and Science Division. I'll be your moderator today, and in a moment I'll hand off things to Professor Will Horwath to present the SMERP slides. But before I do, I want to make sure that everyone knows that this Zoom webinar is already being recorded. Regarding questions during the presentation, please use the Zoom Q&A feature. So it's a typing chat feature. CARB staff and the SMERP will do our best to keep an eye on those comments throughout the presentation and try and answer along the way if possible, or if something is really prescient at the moment. After the presentation, we'll have an opportunity for a more open Q&A via raising hands and unmuting to ask questions or to make comments, as well as to address any additional written chats that remain in the Q&A feature. Also, since we did not receive any requests for interpretation, we don't currently have a live interpreter today, but if any translation of the slides is requested, please let us know and we can have the slides translated and ready for distribution a bit after the meeting for anyone who requests them. And with no further ado, here is Professor Horwath.
All right. Thank you, Kevin. Share my slides. And oops, didn't want that to happen. Oops. All right. Can you see that? Can everyone see that?
Yeah, perfect.
All right. All right. So this is our final report from the SMERP Committee on Nitrogenous Emissions from Soil. Just a reminder that the committee was made of five of us, myself, Dr. Whendee Silver from UC Berkeley, Dr. Xia Zhu-Barker from University of Wisconsin Madison, Dr. Martin Berger, he's an emeritus now, and then Dr. Viney Aneja from North Carolina State University. So I put the slide in. It's in the report. I just wanted to. We didn't have a background slide, so the objective was to evaluate the current science, as you all know, of the different species of reactive gases that come from nitrogen, and one of the issues is that NOx is a precursor to ozone formation in the troposphere, and that's why we have a need to understand these emissions and sources. Just some background again, we were concentrating on soil. There are other sources of emissions. I'll get to a slide on that. But from the soil, it's primarily a biological process, a microbial process, leading to the formation of different reactive end species. They evolve or are produced through the process of fertilization, which can produce volatilization of fertilizers, also through mineralization. Nitrification is a source of these gases, these oxides of nitrogen, as well as denitrification. Okay. So again, I added a slide. It's not in the report, but it's very informative from a study from Dr. Xia Zhu-Barker. There are two pathways to form these reactive oxides of nitrogen, nitrification and denitrification. In nitrification, the substrate is ammonia, which is oxidized to hydroxyalamine. And there we have potential pathways to produce these gases, nitrifier denitrification and nitrification coupled denitrification. There are potentially low levels produced abiotically, depending on the mineralogy of the soil, but it's usually non-significant source in many soils. It can be a significant source in some soils, but mostly non-significant. And denitrification, occurring under conditions of oxygen limitation, which has been mostly associated with moisture, but can also be associated with high microbial activity consuming oxygen. In the many studies that we've done in California, it seems that there's a split, or at least nitrifier denitrification can be an important source of these reactive gases. Okay. Background, you'll see these slides separately in upcoming slides, looking at some global modeling efforts. We see that N2O emissions, depending on where they're from, we have NOx emissions and we have ammonia emissions. Since the substrate for nitrification is ammonia, soil pH and organic matter availability are key factors. And you see high emissions generally in areas, in the temperate areas at least, they're generally where mollisols are soil types. We see these in northeast China. We see these in Ukraine and into the Russian steppe. We see these in Argentina, and we see these in the upper Midwest of the United States. We see that California isn't really showing up very well here, but some coming up slides will be showing it is. It is more of a local thing in California, where the valley, particularly San Joaquin Valley, the Central Valley, is a hotspot. Okay. So again, let me see. Just a summary of how these different reactions can lead to these different products. So nitric oxide, for example, plus nitrogen dioxide can lead to NOx formation in the presence of UV radiation, can form ozone, which is one of the critical things we're addressing here. The reactions of NOx in the atmosphere can lead to nitric acid and fine particulate, 2.5 particulate organic matter. These sources, again, as I said, are soil microbes, and this would be through fertilization, fuel combustion, biomass burning, and lightning. Lightning isn't such an important source in California because our weather system is dominated by low pressure. Some of the things that are emerging that will need to be addressed and will come up in the recommendations are HONO, which is nitrous acid. It's a gaseous form. It's released from soil. It's also produced in the atmosphere, and it can also contribute to ozone production. Sorry. And okay. Oops. All right. So these driving factors, as I said, are both soil and atmosphere, but we're concentrating on soil emissions. We have physiochemical and biological factors driving these emissions, and they all must be considered when we predict these NOx emissions. And that's a challenge. Biology is always a challenge to model. Driving factors and environmental controls vary at short temporal and spatial scales. It's another source of uncertainty. And in agricultural settings, management factors, things like nitrogen fertilizer placement or form of fertilizer or irrigation, as we have in California, which makes us kind of unique compared to the data sets we see across the world. Okay. So again, just keeping on background, this is example. It's a non-irrigated system. It's in Hawaii. And this is just an example from the literature of surface applied versus subsurface applied. And subsurface applied can usually be or is often through knifing of the fertilizer to below 5, 10, 15 centimeters into the soil, depending on the rooting habit of the crop being managed. But we see here that surface application, which is often broadcast fertilizers, lead to increased NO emissions. If you can get good soil contact, you can reduce emissions dramatically by order of magnitude. It doesn't affect N2O emissions as much as we see that it affects NO emissions. Another study under rain-fed conditions in the upper Midwest, we see different forms of fertilizer. Here we have anhydrous ammonia. Here we have urea ammonium nitrate. And then here we have broadcast urea. Again, the broadcast urea showing higher emissions compared to other formulations, such as the anhydrous or the UAN formulations of fertilizer. UAN is what we use in California, but we use it in a micro irrigation system. Okay. All right. Wrapping up the background. So the trends in NOx emissions since 2005, using the GeoChem modeling efforts. We see a general decline overall. Fuel combustion for sure, as we get better controls on our emissions, our combustion processes. But soil emissions have tended to been stable, or we're not increasing, and along with fertilizer and soils remain to be constant over this period. Okay. Again, lightning isn't such a source in California. It is in the mountains, but in the valley, we have low lightning incidences. Just an example of a statistical model, again, background material. I should probably put on my laser. So what I wanted to emphasize in this slide here is that most models, even statistical models, are concentrating on a few factors. As I said, fertilizer type, the amount of N input in fertilized systems, pH, important, is a sort of trigger between nitrification and denitrification sources. We have soil moisture, which is a very important component, and then we have soil temperature. So temperature and moisture regulate by biological activity. pH is a physiochemical process that affects the substrate availability, the amount of substrate added, and then the type of substrate added or fertilizer added affects these emissions. Okay. All right. Let's drill down then in the NOx emissions. Again, where we see intensive agriculture, we see these NOx emissions pop out. So the upper Midwest, the Pampas in Argentina, again, mollisol regions, very productive soils, higher pH soils as well. So could lead to more nitrification, for example. And then we have some in the northeast of China, again on the foot slopes of the Himalayas. And then the tropical environment is temperature and moisture, more of important factors. Okay. So again, these models, we've looked at these models for a while, over 30 years. Yinger and Levy, for example, and then their model was then used in other publications over time. Is the emphasis behind the Berkeley Dalhouse soil NO parameterization model, for example. And these models tend to be semi-mechanistic, empirical models. They have large uncertainties. The uncertainties of some global models have been constrained by observations. particularly from satellite-mounted instruments. Uncertainties of total NOx emissions affect the ratio of soil versus total NOx emissions. The decreasing NOx emissions from fuel combustion increase the soil NOx to total emissions, depending on year. So again, climate, which is temperature and moisture. Okay. So again, continuing on these global models for fertilized croplands, we have the comparison of the statistical and semi-mechanistic empirical models from Viney and Levy, for example. What we do see is we have large uncertainties, and that's the sort of the common thread here, that there's a lot of large uncertainties in these estimates, both from the data gathering stage and from the predicting stage. The level of uncertainty is quite high. Okay. And then finally, we have a comparison here of NOx emissions in the continental US model here, just to show you how we have these different potential outputs from these models. They're, again, leading to this high uncertainty that we see in the published or available public data that we see that we have access to. Okay. All right. So let's now go to California. We're going to be comparing the image model to assess the global environment, the Berkeley, Dalhousie, Iowa soil NO parameterization model, the DNDC, which is denitrification decomposition model. That's a process mechanistic based model that CARB has been using. Again, we see large variability in the prediction. The emission factors have an order of magnitude range as well. And so, again, the bottom line is that the uncertainties are hampering our ability to do predictions and to create good understanding of the sources of these sources of emission. The image model is sort of a tipping bucket model based on inputs of nitrogen and outputs of nitrogen. The Berkeley, Dalhousie, Iowa model is more mechanistic. It has a modified temperature function, for example. And the DNDC tries to incorporate, or does incorporate, excuse me, many biogeochemical processes down to redox, for example, and this informs, and the DNDC model does inform the emission inventory of California Emissions Project Analysis model and its associated data set. Okay. So just to summarize the methodology associated with particularly NOx emissions, we have the chamber technique, which is essentially a soil cover method. It's a static chamber. It measures soil to atmosphere flux. You need a NO analyzer. You can't take the samples back to the lab because the reactants, the products are so reactive, and so you have to measure them in situ. The downfall of a chamber technique, it's a very small footprint, often no more than 30 centimeters of foot in diameter, for example, and you're trying to extrapolate that to a landscape level or a field level, and it's laborious. It's burnt out a lot of graduate students, for example, but there are new instruments coming online and new methodologies, such as the flux tower data. More flux tower data is becoming available, meaning we put these analyzers on these towers and we can have continuous monitoring, for example, above the crop canopy. but then that becomes more difficult to partition sources as but it is a continuous measurement. And so all these things, all these ways of analyzing these things are ways to inform us and to improve our ability to understand. Hono measurements, the nitrous acid, must be done above ground, even though soil is a source. The soil and the atmosphere are both sources of Hono. It requires a specialized analyzer, a long path absorption photometer. There's just not a lot of data on Hono, but yet it is an important intermediate because it's implicated in ozone production. So the tropospheric NO2 concentrations, again, we can use surface monitors and spectrometers to measure ambient concentrations. We can put these on aircraft to sip the air to measure them, in-air concentrations. Pandora is a ground-based system. It's a sun viewing spectrometer to get vertical column densities of concentrations of NO2. And then we have satellite platforms that are the ultimate remote sensing to retrieve total stratospheric and tropospheric into column densities. We have new satellites, Tempo, for example, that have much better resolution, but they have just been recently placed in orbit, geostationary orbit, for example, to get continuous measurements, and their resolution is higher. So we have new data sets that are becoming better over time. Okay. All right. So for direct measurements of NOx, flux, there's really only two sort of comprehensive studies that were done, both commissioned by the Air Resources Board. Matson et al. With Mary Firestone did it back in the mid-90s, and then Berger and Horwath did it in mid-2000s. To look at, we had combining these studies, we had over 4,000 measurements. Over 15 different cropping systems were looked at. Potentially different irrigation and fertility managements were looked at. Studies reported seasonal snapshots of NOx emissions, and average NOx emissions ranged from 0.7 to 2.5 grams of NOx N per hectare per hour. So again, these studies were done with sort of portable analyzers and not using the new approaches, for example, of flux tower measurements or satellite-based measurements. Through the committee's or the panel's review, we identified 5 recent California studies suggesting that CPAM values may be a bit low. The SMERP evaluation criteria were that modeling results were supported by independent data and statistics. We also constructed uncertainties of validation data, such as the uncertainties related to remotely sensed tropospheric NO2 concentrations. The results of these studies have high uncertainties, and that's basically one of the main take-home points of our product here, but nevertheless indicate significantly higher NOx emissions than reported in the CPAM inventory currently being used. All studies involved modeling and were indirect measures requiring additional data to derive the results. Okay. So these studies, these 5 studies are recent studies within the last 10 years. Have a lot of modeling exercises. For example, again, we're beginning to use these eddy covariance methods. And so we're starting to enrich our data sets Again, more eddy covariance methods in these studies. We have ground-based measurements. And then we also have N isotope analysis. So basically, we're using the fractionation of the isotopes, or the N. There's two isotopes of nitrogen, and depending on the process, we can potentially identify soil sources versus combustion sources, for example, depending on the enrichment of the different isotopes in the NOx molecules. Okay. More of this. There's only been one study, and we should have more studies like this in the future. Okay. So again, drilling down to nitrous oxide. You see major emissions in the Midwest. Again, this is the mollisol region, higher soil pHs. Not so diverse cropping systems also. We see less in California, but this is not showing that we're less. The effect is more local, and we still and because of our climate conditions, higher temperatures, we have more ozone produced, for example, than we would have in the Midwest area, for example. So that's why it's critical, and that's why CARB is concerned, because ozone affects not only human health. It affects basically everything. It's an oxidant. It'll degrade your car tires, for example. But the rural communities are sort of more impacted because of their proximity to agricultural fields. All right. So again, harping on this theme of uncertainty, we look at 3 different models to estimate these emissions. The models are sort of good at identifying regions, but you can see the difference in these models. See, I don't have these models identified. Sorry about that. But we see this model, for example, is showing a very strong hotspot. This model kind of picks it up. This model is more diffuse. And so again, the uncertainty in these measurements and the uncertainty of using these measurements in a modeling effort are the prime concerns that we have identified in our panel. Okay. So again, just summarizing the methods, we have chamber-based methods. You can see how laborious this could be. If you're doing it in a flooded situation, for example, you can see what the disturbance factor could be potentially. And here we have these more continuous measurements in these flux towers that can be used. And now that we have these instruments that are becoming more available, more portable, to be able to mount on these towers to get more continuous data. Okay. All right. Going back to the studies, and this is from Berger and Horwath. We've looked at NOx here and N2O emissions. Here we have a furrow irrigated system. Here we have a subsurface drip irrigated system. So this is in tomatoes. We have the effect of cover crop here in both slides. So what we have, the first thing we can see is that under the previous types of management, which aren't dominant anymore, which is a flood, furrow flood, or field flood approaches, we see potentially an order of magnitude higher emissions in both NOx and nitrous oxide. And we see the effect of cover cropped more or less in this slide here in the subsurface drip system. So we have lower emissions, we have higher fertilizer use efficiency, and we have the ability to fertigate, meaning that we can essentially supply nitrogen as the crop needs it, and therefore we increase efficiency of crop utilization dramatically versus the furrow systems, which essentially can only apply fertilizer in one or two events, and that's pre-crop and essentially as you get into the field, get your main fertilizer down. But that leaves a lot of excess fertilizer around until the crop can utilize it. And so that's why we see these differences, and that the micro irrigation systems have kind of led to a dramatic decrease in these emissions. We about a depending on estimates, at least 85% or more of the area now is under some sort of micro irrigation, and we don't see a lot of difference between different micro irrigation systems. So, for example, subsurface drip or micro sprinkler irrigation or surface drip all tend to have similar results with the ability to fertigate, to sort of allow the plant to compete for the nitrogen. Because in these systems here, where you apply the nitrogen in sort of one event or two events, the microbial community can compete for that nitrogen and lead to these emissions. While here, if you can allow the plant to compete it by giving it to it when it needs it, you can lower these emissions. Okay. Again, more examples. So flood irrigation stimulates these emissions. We see here nitrous oxide, a peak in nitrous oxide emissions under flood irrigation. Nitrate increases and along with soil moisture. Here we have an example from the report of an alfalfa. We, particularly in a Martin and Berger study, we looked at alfalfa, and then we followed up in a Burns et al. Study as well. It's not fertilized, but the system does produce a lot of nitrogen. And as these stands age, they produce more and more. Their emissions can be even higher than a fertilized system. And so when we look at flood, which is the normal practice, business as usual, versus subsurface drip, we see that the subsurface drip system can dramatically reduce nitrous oxide emissions. And when you look at the cumulative outcome, we see a dramatic reduction. And so the industry, by adopting micro irrigation, is on the way to reducing these these reactive nitrogen emissions because of the enhanced fertilizer use efficiency and placement, and also formulations. Okay. So particularly in Assembly Bill 1757, the Natural and Working Lands Act, and some other related legislation, diversion of organic materials from landfills, for example, and shunting those towards composting efforts with green waste. We see in general, compost has no effect on nitrous oxide emissions. We don't have a lot of data on NOx emissions in compost, unfortunately. But the effects of compost are such that they don't really affect emissions, and in many cases decrease emissions, even if it's only surface applied. And so we have that another potential solution to reducing these emissions through the use of compost. Okay. All right. Wrapping it up on these are products here, ammonia emissions. Again, we see the upper Midwest has high emissions. They have mollisols. They tend to be higher soil pHs, leading to ammonia emissions. In California, we have arid soils, which tend to also be higher pH, and we can have also high ammonia emissions as a result as well. Okay. So ammonia emissions vary across inventories. There are new analyzers coming out. One of the main problems with determining these inventories is the analysis, the analytical methods available to us. But we are beginning to get analyzers now, laser-based analyzers, and portable that they can also be mounted on these flux towers, for example, and they can start to address this uncertainty in the ammonia emissions. In California, agriculture is the dominant source of ammonia emissions, and that's both from fertilizer and animal operations, for example. And in the Central Valley, they contribute disproportionately to these emissions. Ammonia volatilization from soil is highly variable. As I said, is influenced by pH, but other factors such as moisture, temperature, and end management complicate the measurements, mitigation efforts, and constructing these data sets. All right, so I'll go on to the recommendations now. So the SMERP recommends obtaining additional data because of the uncertainty we see in the data sets and the modeling efforts to date. So more data is needed to improve model parameterization and model outputs. Currently available data are temporally too sparse, particularly to validate process models like the D&DC model. So uncertainty in the data sources leads to uncertainty in model prediction. So future assessments of soil NOx emissions must take advantage of the multiple measurements and monitoring approaches together to address the uncertainties of soil NOx emissions. So all the platforms, satellite platforms, flux tower platforms, and chamber measurements, but again, more continuous measurements, more seasonal measurements is the limitation here. So there's a need for continuous or frequent measurements. Chamber-based measurements are hard. They're laborious. You could get one or two observations a day. Because they're so laborious, they come in, the interval between measurements tends to be weeks or daily to weeks. If you want to try to get an event, for example, an irrigation event, you try to get out the day before the irrigation, a day after the irrigation, and a few days after the irrigation to try to follow the flux curve. But again, that's a lot of work. And so now, but with the new instruments and the ability to do continuous measurements, we can start to address those concerns. This would mitigate the limitation of the small surface areas of these chambers, which are the majority of the data in the literature so far. But again, that will change now as these flux tower data become more available. Other considerations of the location of fertilizer placement must also be considered, for example, in chamber. They don't need to be considered in the flux chamber or flux tower measurements, for example. So again, emphasizing continuous data capture that would capture these hot moments of emissions, because you can't just go into the field and get a measurement and say that's good. These emissions occur in bursts, and they are related to events like fertilization, irrigation. And so if you have continuous measurements, you can capture those. The chamber measurements are hard because you have to identify those potential periods and actually go out and measure them. While here, the continuous measurements are more automated. To cope with the uncertainty in predictions, we recommend installing additional ambient NO2 monitoring sites in rural locations. Currently, almost all of these stations are located in urban environments or near highways. Integrated measures of the effects of NOx emissions on air quality provide the inventories of the other ambient NOx sources. It could improve accuracy, essentially, if we could get a better understanding of the sources across the landscape. And to validate these estimates of NOx estimates, we should locate them in areas where we think there will be higher emissions, and then combine those with remotely sensed data. So for example, as I mentioned, within the last couple of years, Tempo is a geostationary satellite, which gives us much higher resolution, gives us hourly data at a still somewhat a coarse resolution, but much better than previously. To better parameterize these models, and maintain an updated database, and fertilizer use and application times is recommended. This data is actually hard to come by, but now with the Irrigated Lands Program and SGMA, the California Water boards do collect this data now. And so we have to aggregate this data. It's not readily available. And so the agencies, we encourage the resource agencies to start talking to each other to share these data sets. And then the information on and fertilizer application timing can be also obtained from some University of California, particularly from the cooperative extension side of it, because they're in the field and understanding these systems, and also have some data as well. All right. So our recommendations for research topics, as I said, HONO, nitrous acid, is a hydroxy radical, very reactive, and can lead to high levels of ozone production. Ammonia-based fertilizers or ammonia-based fertilizers can be strong sources of this. Again, the industry moving towards these micro-irrigation systems are using formulations of urea, ammonium, and nitrate. And so they're still ammonia-based fertilizers, but they're used in micro-irrigation systems. They're more efficient, but still, there's still potential for emissions, even though they may be orders of magnitude lower. And so they still affect ozone production, for example. And to capture these bursts or hot moments, particularly in re-wetting soils, particularly in forage production systems where flood practices are still used, that is also changing. I've worked with dairy operators to look at, for example, subsurface drip in their forage production systems. And again, that reduces emissions dramatically. We're now processing manure it won't be across the industry, but at least it's happening, is we have anaerobic digesters. And so the materials that are coming out of these operations, these animal operations, can be more predictable now with more processing. So again, that should lead to better or more efficient nitrogen use. Okay. So as I said, ammonia emissions, these instruments are becoming available, so they should now be deployed to enrich the data sets, enhance the data sets. Research should focus on soils amended with manure and digestates and nitrification and urease inhibitors, and soils under subsurface drip irrigation. Continuous nitrous oxide flux to capture hot moments improved. So instrumentation is improving, but we need to get those out there now. Those instruments are now available, but we need to get them out there, particularly in the rural settings. Okay. I think that's close to it. And this is the sort of summary figure that in the report to help inform CARB. So again, it's we need to capture these pulses. We need data on the amount of fertilizers applied, when they're applied, what types are applied. We need to use new methods such as stable isotope methodology, more aircraft-based operations, more rural or ground-based monitoring, for example. All these are needed to try to estimate total emissions to get a better handle on the inventory. So with that, thank you. The panel had a great time putting this together, and now it's time for questions. Okay.
Great. Thanks so much, Will.
Uh,
We right now have 16 minutes, and I wanted to run through a couple of the chat comments and then go to hands raised, and I'm keeping an order of things. So first quick question was from Kevin Williams. There was a earlier slide, and I think it might have been slide 10 on your deck, but it's just what does the M stand for? And I think it was in relation to subsurface drip irrigation and fertilizer mixing, but it was kind of hard to find where that M factor was.
Okay, hold on. Slide, which slide?
I think it might have been 10 on your deck with that extra slide injected. And I can't find the M reference. I just saw soil moisture.
No, that was under rain-fed conditions.
Okay.
Okay, I was going to just say, I think it might be an atmospheric reaction where M is the third body that absorbs excess energy.
M.
Right. So it's not part of the reaction itself, part of a atmospheric molecular reaction in the atmosphere with oxygen, but it absorbs excess energy. So it's just a third body in the equation.
Oh, I think it was slide 7 in your, that's right. It was on that little, yeah. So, okay, that makes sense.
Oh yeah, and okay, yeah, it could be N, or it could be any, it could be a particulate, a fine particulate matter. It could be a number of different things. M stands for a lot of different things in that.
Okay, cool. I think that covers that first question. The next question is Heather Lieb. She asks, is UAN used universally throughout California or just in the Sacramento Valley? Have we made any progress with gaining access to the total nitrogen applied, the TNA reports for ag regions for the Water Resource Control Board? So her second question, I have written them a couple of times, haven't gotten traction on that, so I will write again. So with her first question, can someone answer that? And then also, if anyone on the panel has connections to getting those total nitrogen applied reports, that would be awesome.
Well, UAN is used kind of preferably in micro irrigation systems because of essentially keeping neutral charge in crop uptake. So you have ammonium and you have nitrate, and that maintains a neutral pH in the root zone. And that's why UAN is preferred, and it's preferred in micro irrigation systems. And so wherever you see micro irrigation systems, you'll likely see some sort of formulation of UAN. Again, that's one of the second part of that available data for fertilizer application is one of our recommendations. No, the resource agencies need to start talking to each other and share their data sets, or make them available in a way that they can be utilized. And so that is probably, it could be a heavy lift, but it's one of our recommendations.
Great. Thanks so much. Our next question was Gabriel Ludwig asks, can Dr. Horwath go more into the very wide range of emission factors in the different models, the 15% versus less than 1%? Any idea what drove the choices made?
All right. Martin, do you want to?
I didn't quite understand. What do you mean the choices made? These are, that slide, these were the 3 models that were published on California emissions. And the first one, that emission factor of 15%, that was calculated from the data in the paper. They didn't. The second model, BDISNP, that was a modified. It was slightly modified by increasing the actually the modelers, they increased the emission factor to 2.5%.
Right.
And also increased the temperature function. And then they came up with a very similar overall emission rate as in the image model. the DNDC model, that is a process-based, that was totally bottom-up. That was process-based model. But there was a problem with the validation, because these data sets that were used to validate the model, they were not really adequate. They were temporarily too sparse. So one thing I can say about these models is that, even the DNDC model, it is mechanistic, but it can, of course, it cannot measure, or it cannot predict at an exact moment how much NO is emitted. And how could it even do that? Even if it was perfect, it couldn't do that, because we have this landscape with all different crops, different timing, etc. So in order to validate the DNDC model, you need to have a period, and that was actually attempted. So it has to be the whole season, and so we can get averages that are approximately right. So, and yeah, that's how these models were formulated. So the image model is a much coarser model. It's a totally different system. It's based on inputs and outputs, and it doesn't really take into account the timing. We have a lot of responses to fertilizer, so it is assumed that all these emission factors, they can all the surplus can potentially be emitted, depending on what the moisture level is. And just based on these values, the emission factor is really high. One thing we can say, if this is really true, that the emission factor is 15%, then farmers would actually also see it in their yields. If that is such a big loss, that is a pretty substantial loss of N.
Yeah, that's a good point.
Kevin,
I didn't quite understand all the nuances of the question, but I let Viney speak.
Viney. Go ahead, Viney.
Our panel.
Kevin, may I go ahead and?
Yes, definitely.
Okay. I want to just add to what Dr. Berger articulated, and what he's articulated is quite correct. But what I want to add is that perhaps the person asking the question is, and I don't know if that is the intent of the person asking the question, is that the emission factors, how come they are varying from 15% to about 1%? Well, depending on the technique that has been used to calculate the emissions, and then the emission factor will have a response to the emission factor. But I want to put the person at ease. If they are only concerned about 15% variation in the emission factor in observed measurements, that is reasonably good. And we ought not to be so concerned that the range is between 15 and 1%. That's pretty good for observation-based analysis. But the values, if they are changing in that range, is because different investigators may have used different techniques to calculate the emission factors.
Thanks for that. I think we'll probably move on to more questions, because we have piled up 12 total questions, and we only have 6 minutes, plus we have a hand raise that we still need to get to. So I'll try and rush through. So Heather Lee was questioning about other regions for irrigation practices, and I think that's more of like a water board, regional water board kind of question. But yeah, I think we'll probably have to do a lot of like written responses to questions just to kind of get through. But I know someone asked about theories on how compost can decrease N2O emissions, which I think is a pretty large discussion. So we'll make sure to have that on our radar to address later. And then Gabriel Ledwig asked, to what extent do we see differences in various nitrogenous emissions in winter versus summer months, like rainfall, breakdown of organic matter, et cetera? Do we have a rough summer versus winter in let's say the Central Valley for N emissions, especially NOx?
For NOx, we don't have any data in the winter from California.
Okay. And so,
we focused that time when we did the survey in 2013, we focused on the summer because of the ozone, the effect of the ozone. Then in the winter, even we thought there is less potential for ozone because there's less intense sunlight. And also in the summer is the fertilizing season. That's why at that time, that's why we focused only on the summer. But there is nobody has measured it in the winter.
Mm-hmm.
That's good to know. That's a big need. I mean, really, we know 365, we have need there. Okay, we have another question about hoping for a list of data or variables that would be helpful to collect the ILRP to optimize these models.
Could you repeat that again? I didn't understand.
Would it be possible for a list of data or some variables to be put together or shared that would be helpful to collect for the ILRP to optimize these models?
What is ILRP?
I did not Google it, so I am not familiar, but we can skip that and answer it later if we're not familiar with the acronym. Okay, so we have 4 minutes. I think we're now down to the hand raise. So Ian, I will unmute you. Hold on one sec while I figure that out. And allow to talk, and you can unmute. There you go. Okay.
Yeah. Hello. Thank you for giving me the opportunity to respond. My name is Ian Faluna. I'm a professor of atmospheric science from UC Davis. And as you probably might have guessed, I'm very disappointed with this final report. There was a limited window to give responses to. I gave a bunch of responses to, most of which were ignored. So I would like to just state for the record that the public should not consider this report on par with a peer-reviewed study. It's filled with technical flaws, in my opinion. I have a lot of those which I could get into, but we have only a couple minutes. First and foremost, however, NOx produces ozone and it produces PM 2.5. And there was a CARB-funded study done by Professor Michael Kleeman at UC Davis, that indicated that the PM 2.5 in the wintertime, that their modeling of that was improved when they put in the soil source from the image model from the Alvarez et al. Study. A bunch of other issues I have with this report, but it's, like I said, there's not much time here. I went on to just mention this emphasis on uncertainty is without any attempt to quantify what that uncertainty is. It's right out of the playbook of the tobacco playbook for climate deniers, for ozone hole deniers. This is, in my opinion, this is a tried and true method to just sow confusion and delay regulatory response. And the reason I'm so disappointed is because CARB built its estimable reputation by combating the automotive industry, but now seems unwilling to take a critical look at agriculture in the state. And this idea that there was 5 studies that indicated that the current CARB inventory is low is a large undercount. I count 11 studies. I've given it to the panel. They didn't include them. I don't know why, but that's just a disagreement. The panel's primarily made up of people who were involved with disagreeing with the results from Alvarez, and also Professor Aneja, who put out a model with extremely small NOx emission rate, which has an unrealistic temperature coefficient in it. And so I feel like specifically this panel is not equipped to really look at it holistically, to look at the problem holistically and try to address all of the issues
So
that are
Ian,
out there.
Sorry, this is Kevin. We only have like 30 seconds left.
Yeah, I just wanted to
and-
get that in the record
Yeah.
because I believe this report is a real disservice to the taxpayers of the state who spent $200,000 on a report that says we don't know anything, that we could be 1%, it could be 50%. That's an order and a half magnitude spread with no estimate of what the actual most likely value is, which you can absolutely do statistically in a meta-analysis. It's very commonly done.
Ian, sorry,
So
we're
thank you for
completely out of
giving me
time.
the opportunity.
Thank you. Thank you for the comment. I just want to make a quick follow-up that moving forward, CARB will be brainstorming on a research project with nitrogenous emissions from soils based on the final report, and we will welcome any additional comments that you have but did not submit during the draft final review process. If you have any additional comments on research, we welcome and encourage you to email us at research@arb.ca.gov. We'll be in touch, and our plan for the first step moving forward will be to have an email like we've been doing, a direct email for all SMERP workshop participants to start the next steps of discussion. And we welcome everyone obviously to this table, and we're sorry we ran out of time. We will be in touch on any additional questions that weren't able to be answered because of our time frame. And thank you so much for participating. Sorry to keep you 1 minute over. Thank you, everyone. Thank you to the SMERP for the final report. And thank you for everyone for making comments and participating. Thank you.